I'm Michael, and I will be presenting one of our target problems from today. So let's take a look at target 6. We have how many positive whole numbers less than 1,000 are relatively prime to each of the 5 smallest composite numbers. Now, let's first take a look at some of the terminology here. Relatively prime means it shares no factors with another number other than 1. And composite numbers are numbers that are not prime. That is, they have at least 2 distinct prime factors, or rather, 2 not necessarily distinct prime factors, excuse me. So the 5 smallest composite numbers are 4, 6, 8, 9, and 10, because 2, 3, 5, and 7 are prime, excuse me, and 1 is neither prime nor composite. So if we look at these, right, we can prime factorize each of these numbers. We get 2 squared, 2 times 3, 2 cubed, 3 squared, and 2 times 5. Now, the key point with this is that if a number is relatively prime to all of these, then that means it has no factors of 2, 3, or 5. So these are the forbidden factors, I guess we could call them, that we want to find. So we want to find the number of numbers less than 1,000, the number of whole numbers less than 1,000 that do not have any factors of 2, 3, or 5 in their prime factorizations. Now, how do we do that? We can use a nice tool called pi, or the principle of inclusion and exclusion. Now, what is that? Well, it's basically a fancy way to say we're going to start with our total, and we're going to subtract out all of the numbers that don't work, and we're going to add back some numbers that do work, and so on and so forth. So how do we do that? Well, let's take a look. So we have a couple categories. We have numbers divisible by 2, 3, 5, 2 and 3, 2 and 5, 3 and 5, and 2, 3, and 5. Now, you might be wondering, Michael, why do we need to do all of these? And we'll take a look at why in just a bit. But to figure out how many positive whole numbers less than 1,000 are relatively prime to each of these, we need to find out how many numbers less than 1,000 are not relatively prime to each of 2, 3, and 5. Now, for our purposes, we can assume that less than 1,000, right, we're going to turn that into less than or equal to 1,000. Why? Because 1,000 doesn't count anyways. So if we just go to 1,000, right, it makes our life a lot easier, because we can say the number of positive whole numbers less than or equal to 1,000 divisible by 2 is 1,000 over 2, which equals 500, right? For 3, we take 1,000 over 3, and we take the floor of that. And the reason we take the floor is because we don't have fractional numbers, right? We can't have a fractional number of numbers being divisible, being relatively prime. So the next one, we have 1,000 over 5. That gives us 200. Now, the reason that we need to include the other ones is because if right now I say that I have 1,000 numbers, right, and I need to subtract out the 500, the 333, and the 200 numbers that are divisible by each of 2, 3, and 5, then I will end up with a total of negative 33 positive whole numbers relatively prime to each of the 5 composite numbers, and we know that that isn't true because I can't have a negative number of numbers. Now, why is that? That's because when we take out the number of numbers divisible by 2, 3, and 5, we double count the numbers that are divisible by, say, 2 and 3, 2 and 5, or 3 and 5. So we're going to divide 1,000 now by the least common multiples of these pairs of primes. And since 2, 3, and 5 are each relatively prime to each other, since they're all distinct prime numbers, that gives us 166 multiples of 6. 1,000 over 2 times 5 is just 100. And the floor of 100 over 3 times 5 gives us, what is that, 66. Now, we can add all of these back to our number. These are all of our double counts. But in accounting for double counts, we have now over-accounted for triple counts, because now we've added back the number of all of the numbers that are divisible by 2, 3, and 5 one extra time. So we have to subtract that out. And this is a general part of pi, or the principle of inclusion and exclusion as well. You just start by subtracting all groups of 1, add back groups of 2, subtract groups of 3, so on and so forth. So we take 100 divided by 2, 3, and 5, take the floor of that. That gives us 33. So we have to add 33 numbers back. Right, and that will give us our total. And if we do that, we get, what is that? I believe you get a total of 266. Let's check the math there. That should be a minus. Sorry, I wrote that incorrectly. And you should get an answer of 266, I think. Let's check that. Negative 33. Yep, so 266. So we get 266 total numbers, less than 1,000, that are relatively prime to each of the 5 smallest composite numbers. Now, another way we can visualize this is by drawing a Venn diagram. So if you just say that the numbers divisible by 2 are in this circle, 3 in this circle, 5 in this circle, right? We can essentially say that when we subtract out each of the original ones, we're subtracting out the whole circle. So we subtract out all 3 circles, right? Which means that we take out everything in the shared regions multiple times. So then we add back everything in the shared region, but that means that we add back the middle jointly shared region between all 3 too many times, and we have to subtract that out one more time. So that's essentially a visual demonstration of what pi looks like. All right, cool. So we get 266 numbers as our answer for this one.
Hey, this is Tim. Hope you're enjoying our videos. If so, you know what to do. Like, subscribe, turn on notifications, all that sort of thing. But what I'd really want to invite you to do is to send us an email at media@mathleague.org. Tell us which problems you'd like to see us cover next in our video series. Take care and see you in the next video.